Imagine stepping into a crowded, incredibly loud room. Now, picture putting on a pair of high-end, noise-canceling headphones. Instantly, the chaos drops away, leaving you in perfectly clear, focused silence. In the world of physics, traditional magnets act like that noisy room. Even though we can't hear them, they are effectively loud, constantly broadcasting invisible magnetic fields outward in every direction. This behavior creates a challenge for modern electronic design. To make our phones and computers faster, engineers need to pack the internal parts as tightly together as physical space allows. This animation shows what happens when those parts get crammed together. As the components emit their invisible magnetic forces, the fields overlap and crash. That clashing creates a storm of magnetic noise. This interference can scramble data, generate heat, and drain your battery. To push our devices toward further miniaturization, we need a different kind of material. We need a magnet that holds its powerful force inside while remaining completely silent to the outside world. Chemists have developed a solution using a class of materials known as metal organic frameworks, or MOFs. You can think of a MOF as a highly customizable, microscopic set of Legos. By picking the exact right pieces, researchers have built a specific MOF that functions as a noise-canceling magnet. It is strong on the inside, but produces virtually zero external magnetic noise. This diagram shows how the material is built. The corners of this repeating grid are chromium metal atoms, joined by straight, organic linking molecules. Each building block is magnetic. When they snap together, they lock in significant internal tension. The precise geometric arrangement of these specific molecules is what finally traps the magnetic energy inside the structure. Inside the grid, the metal atoms generate a magnetic force pushing upward. Simultaneously, the organic linking molecules push back with an equal downward force. Locked in a balanced tug-of-war, these opposing forces cancel out, making all external magnetic forces disappear. This works just like noise-canceling headphones, listening for an incoming sound wave and creating an inverted wave to erase the noise entirely. Scientists have created self-canceling magnets before, but older versions only functioned at extreme sub-zero temperatures. This newly engineered MOF remains stable at room temperature. Achieving this internal magnetic cancellation at everyday temperatures gives engineers a noise-free building block to design the next wave of technology. This silence is exactly what a field called Spintronics needs to work. Spintronics is the anticipated successor to standard electronics, though it remains difficult to build because of a specific physical limitation. In standard electronics, devices transfer data by physically pushing the electrical charge of an electron down a wire. Moving those particles creates friction, which wastes energy and generates heat. Spintronics avoids friction. Instead of pushing the electron from point A to B, it stays in place, transferring data by changing its spin direction. By keeping particles stationary, we bypass heat, cutting energy waste and allowing processing speeds that leave traditional circuits behind. The leap in efficiency is like moving from tapping out a slow Morse code message to instantly streaming a high-definition movie. The difficulty lies in how fragile an electron's spin state is. If it is exposed to even a tiny amount of outside magnetic interference, the spin scrambles and the data is lost. That sensitivity is why the discovery of a zero-noise magnet matters. It provides the silent environment that spintronic devices require to function. By building components out of this stealth material, engineers can pack those spinning electrons closer together without any risk of them scrambling each other's signals. For the consumer, this means smartphones that barely drain their batteries and computers capable of processing speeds previously thought impossible. Building faster and more powerful devices depends on more than shrinking components. It requires absolute magnetic silence